You will see a demonstration of IMPACT's capabilities using visualization tools AMDA and 3D View and their interconnection with simulation databases through the study of kinetic aspects in the Martian environment, in particular the research of evidence for O+ ions plume. Mars lacks of a global intrinsic magnetic field, and consequently the plasma ejected by the Sun, the solar wind, interacts directly with the Martian atmosphere. Mars, like Venus, possesses an extended oxygen-neutral corona, which can be partly ionized by solar photons, solar wind electron impacts, or charge exchange with solar wind or planetary ions. The newborn ions outside of the ionosphere are called pickup ions and are initially almost at rest in comparison with the solar wind. These ions are expected to be accelerated by the motional electric field produced by the solar wind bulk velocity and the interplanetary magnetic field. Farther they are from the planet, higher is the energy expected due to longer time acceleration. We start this study by searching an event of accelerated oxygen ions in Mars' vicinity using AMDA, the Automated Multi-Dataset Analysis Service, developed by the Plasma Physics Data Center, CDPP. AMDA is helpful to make simple representations of time series of in situ observations in the domain of space plasma physics, and it is an excellent tool to browse the data and look for events. We will use AMDA to study Mars express charged particle observations. To do that, we will plot protons and heavy ions spectra observed along Mars express orbit around Mars. We will also display the ephemeris in cylindrical coordinates. Data are available on CDPP database and can be plotted simply by dragging the parameters of interest to the plotting window, meanwhile indicating the time interval of interest to us, namely the 17/12/2004 between 17 and 19. Then we click on Plot. Mars express trajectory in a cylindrical coordinate system is presented in the bottom panel. Different empirical boundaries are seen, such as the induced magnetosphere boundary, close to the planet, and the bow shock, farther. For this time interval, Mars Express seems to be located all the time downstream of the BS. The proton energy spectra confirms that the spacecraft is mainly located in the Martian magnetosheath region, which is the region located between the Martian-induced magnetosphere and the solar wind. On the inbound pass, presence of heavy ions is clearly seen. We can also see a dependency of their energy signature. Closer to the planet Mars Express is going, less and less energy the heavy ions have. Such signatures are expected for oxygen pickup ions in the hemisphere where the convection electric field is pointing outward the planet. Secondly, we intend to check this feature view with a 3D visualization scene and hybrid simulation results. The application 3D View is well adapted to this task. This tool offers immediate 3D visualization of position and orientation of spacecrafts, planetary ephemerides, as well as scientific data representation. It is available to download on this web page. We launch 3D View, open a new file, and manage a new scene. In the selection dialog window which shows up, we select the time interval and the Mars Express spacecraft to load the ephemerides. By clicking on OK, the Mars Express trajectory during the selected time interval is loaded in 3D View. We click on Go to display the spacecraft and visualize its motion around Mars. It is possible to play with different display options, like the thickness of the spacecraft trajectory and the size of the spacecraft to make it more visible. We can zoom, enlarge, and rotate the scene to understand the 3D perspective. We load a Bowshock model. So far, the Chotanyan et al. 2006 is the only one available in 3D view. Other might be available later in the project. This 3D Bowshock allows us to determine roughly if the spacecraft is in the solar wind or not, and which part of the trajectory is expected to be downstream of the Bowshock. For this example, it seems that the trajectory is completely located downstream of the Bowshock, in agreement with AMDA observations. Now we will look at the O+ density in the vicinity of Mars. With the IMPEX facilities integrated in 3D view, we can load a 3D cube corresponding to a numerical solution for O+ density, obtained with a 3D multi-species parallel hybrid code developed at Latmos. Thus, on the Science menu displayed on the toolbar, we select the IMPEX tree option. This option opens the IMPEX parameters selection window. Let us choose the Latmos/Mars_14_01_13 simulation data product and focus on the O+ density. We can now load data in the 3D scene. We refer to the Latmos hybrid simulation web page in order to have information concerning this run. By selecting the same run ID, then on the 3D view tree, several information are indicated. They present the basic parameters for which the run has been performed. Other indications are not listed here, but could be useful for this study. The interplanetary magnetic field lies in the XY plane, meaning the motional electric field points northward. Once the O+ density cube is loaded, by adjusting the max and min values for the color bar and moving the different 2D cuts at different levels, we have a 3D view of the O+ ions density distribution. An asymmetric picture is emphasized, and we can find two escape channels for the O+ ions. The main escape channel is directed toward the region where the induced magnetosphere is stretched in the unite side, the magnetotail. The other escape channel corresponds to the O+ ions plume in the northward hemisphere, where O+ ions are accelerated by the motional electric field. By playing on the different cut levels, we see that during the inbound part in the northern hemisphere, the spacecraft flies through the O+ ions plume, while on the outbound pass in the southern hemisphere, less O+ density is noticed. So far, simulations are consistent with the expected behavior and Mars Express observations. In order to have a confirmation that the speed, energy of the O+ ions are more important farther from the planet, we will display the O+ velocity module cube. We select now the O+ velocity module in the IMPEX parameters selection window and load it in the 3D scene. Then, we adjust the min and max values of the color bar. The northern-southern asymmetries are more pronounced. The northern hemisphere, which corresponds to the region where the electric field is pointing outward the planet, is the hemisphere with highest O+ ions energy. We can clearly see the ion plume and imagine the acceleration due to the motional electric field. On the inbound path, the spacecraft is crossing the ion plume, where high speed energy is indicated by the simulation. Going closer to the planet, the speed decreases. On the outbound path, the spacecraft passes a region where low speed and energy of O+ ions are present and is consistent with the lack of signatures on Mars Express data. Finally, the presented scenario demonstrated how to identify interesting events and have a better understanding of the different physical processes involved by restituting the observations in a 3D scene. This was performed a simple way thanks to interactive framework facilities developed by IMPEX team. Thank you for your attention.